So I said in the last lecture that the crucial bit is saying how you're going to model H1. So that's what I want to think about a bit more in the workshop and get you to practically do it. I can give you the link to the software and you can play around with it. So just to give a little bit of motivation again, I don't know if you've seen the dance of the p-values. Jeff Cummings has on his website, Melbourne psychologist, he has some Excel macros there. And what this is here is simulations of the same study done over and over again. There really is a 10-point difference in the population to pick up. There's a 50% power to pick it up. And the point to look at is on the left-hand side here. So the first simulation, I just ran it, I took a grab of the screen, and this was it. So the first simulation I got here was a P of 0.23, 0.144. So half of these will be significant and half of them won't, which is what it means for a power of 50% when there really is an effect there, and what is estimated to be typical in psychology, or even worse. Now, the thing to notice about the dance of the p-values is how you could get 0.006 in one study there, which you'd feel that must be an effect here. You'd be absolutely delighted. And the very next study, without anything changed, and we know nothing has changed because this is a computer simulation, so it's nothing to do with it was a different time of term, it was a different research assistant running it, etc., etc. A P of 0.476, which would probably leave you depressed, saying, what the hell is going on? 0.476 is really non-significant, and so on. So p-values just dance around in this way. So we have 0.03 here, followed by 0.74. Which goes back to the point I said earlier about 0.74 doesn't actually constitute evidence for the null hypothesis. Because in each of these cases, by assumption, there is a real effect. So as Jeff says, I think it's just good for the soul, really, to have a look at the dance of the p-value, just to know and sort of internalize that is what you should expect with the real data of the sort we typically collect, with 50% power. And of course, if you're doing fMRI, Barton et al. Estimated 10% power, or thereabouts, so it's not always as good as 50% even. So I suggested the solution to this was the Bayes factor. At least one solution, doesn't solve all our problems, but I think it's part of the solution. And I pointed out the Bayes factor is the amount by which you should change your prior odds. Now, prior comes up in two ways in discussion of Bayes, which is why I didn't use the term prior at all in the previous lecture, because I only use the term in one context. Here I've used it as your prior odds, and that's just personal. That's up to you how much you believe in the theory or not. So if you take something like subliminal perception, some people might say, yeah, I find that very plausible, and other people say, no way will I accept subliminal perception. Right? So people start with the various theories in psychology or neuroscience with different prior odds about how much they were willing to believe in that theory. Well then, so that's the sort of subjective part, and then there's the Bayes factor, or the evidence, which tells you how much you change that opinion. Now, given you accept the assumptions that goes into the Bayes factor, say it's 5, then no matter what your starting point, you multiply your odds by 5. So everyone moves by the same amount. So in that sense, that's what's subjective. Although it's objective, various assumptions go into it, though. And I said one of the assumptions is how you model H1. And that model of H1 is also sometimes called a prior. So that's what figures. So prior figures in here in terms of modeling H1. In other words, specifying what does your theory predict. But for me, saying what a theory predicts is a different sort of beast than saying how much I believe in a theory. So I reserve the term prior for your prior belief in the theory, and specifying what your theory predicts, I call the model of H1. Now, it's not that that is devoid of any subjective elements whatsoever, because it's a matter of scientific judgment, ultimately, in saying this model is a good model, adequate model of the scientific situation, in specifying what the theory predicts. On the other hand, as long as you make all of those assumptions explicit, which you do, so when you specify this model of H1 as, say, a half normal, you've made explicit what your model is. And what you should always do when you give a model like that, like you say, I'm going to use the half normal, the standard deviation set to something, give a reason. The reason is because this study got that effect size. Now it's a matter of the public record, not only what decisions you made, but why you made them. And therefore it's a matter of possible public debate. And that is just the nature of science. So that's why specifying what your theory predicts and why is a different sort of beast for me than how much you believe in the theory. One is necessary for the process of science, and the other is just your personal beliefs. So scientific judgment actually goes into especially your model of H0 and your model of H1, but in the end you also have to make a judgment whether other data are sufficiently normal to justify using that as a model of your data or whatever probability distribution you want to use. So now, having made the judgments that these are adequate models on a largely scientific basis, then the strength of evidence, you have the guarantee of the axioms of probability that you're getting the strength of evidence back in the Bayes factor for your model of H1 versus H0. So what I said was, in modelling the predictions of H1, we wanted to use assumptions that are informed and simple. And if you remember this example, we have some study that's relevantly similar to a further study, might be the best example you can find. So you use that to specify a scale of effect, without being committed at all that this is exactly the right amount. You're just saying this is the right sort of scale of effect. It's 5 seconds, it's not 50 seconds or something else. And I then argued for the particular model I used last time, well, I think we have good reasons for thinking published effects, or even effects that catch your eye in your own data, are overestimates. So let's presume smaller effects are more likely than bigger effects. And I also assumed a 2-to-1 ratio of the maximum to that scale. And that with those assumptions, we came up with a normal or half normal. But I want to give you some other options here, because there's no reason why these particular assumptions should be the best way of looking at things. So let's consider another example. You might be interested in whether imagining a sports move improves sports performance. So you get a bunch of people to imagine swinging a golf club and hitting a ball, and they do that for 20 minutes a day for a week, and you measure the amount of balls in the hole before and afterwards, and you get a non-significant result. Well, a non-significant result by itself means nothing, right? Whether you're a Bayesian or not, you would have to have some idea, some handle on the sort of size of effect you're trying to pick up to possibly know whether a non-significant result meant anything or what it might mean. So what I would suggest you do, and using Bayes factors has motivated me, and I hope motivates other people, often to collect more data to inform me about what I would expect in a given situation. So in this case, I think relevant data, which would be highly informative, just intuitively speaking, no matter what one's statistical persuasion, would be how well do people do if they really swing a golf club and practice, right? So let's say you had a control group that actually swung a golf club 20 minutes a day for a week, and you measured how many more times they got a ball in the hole. I think that's probably the maximum you could expect. It might be as good as that, but I don't think imagination will be better than that. I'm not in the area, but that's my feeling. Anyway, that's something about which you make a scientific judgment. So what would be the sort of simplest way of respecting that intuition? Well, you could assume any population effect of imagination from 0 to that maximum is possible. And you might say, well, why don't we just say equally plausible, just to be simple. So then that's how you get a uniform distribution. Sometimes when you look at other studies, you think, well, that's, as came up in the question before, maybe it's not a good estimate of the sort of effect I expect. It might actually be a maximum effect I could expect. For example, if you had some population that was impaired on a task, the controls might define a maximum you could expect for that population to perform on the task. So if the people really swinging the golf club and you ran a ton of them and got a good estimate, got 8 more balls in the hole post versus pre the week, we could have a uniform from 0 to 8. I use 0 as just sort of as a default bottom value there. You might want to put in a minimum. What I found that for plausible minima in the cases I thought about, it really didn't make much of a difference, hardly at all, to the Bayes factor. But the Bayes factor is sensitive to the maximum. But that's precisely what we've got an objective handle in, and then I can point to a figure and say, that's why I chose that value. Right? I didn't just arbitrarily come up with it. It's what this group did. So the 2 rules of thumb that get me by, I don't know, at least 90% of the time are now the 2 that I mentioned. Either I think from some past study, meta-analysis or something like that, I can get a handle on the sort of scale effect that I'm interested in which case I use a normal or half normal with the expected value from that meta-analysis or past study, setting the standard deviation, as I went through before. Or sometimes, and maybe almost as often, I think of why there's some good estimate of a maximum, and then you could do a uniform up to that maximum. Or you could do a half normal with a standard deviation equal to half that maximum, which I think is actually probably a little bit better. But I've often gone with the uniform just because it's the simplest way of specifying to reviewers and readers a distribution that reflects a maximum value. Feel free to interrupt, by the way, if you have any questions as I'm whipping through this. So now if you look at the Bayes factor calculators that are on the web, what my one offers is uniform, normal, half normal, and I put up R code for also using t-distributions. The other, what you have in JASP and the Rauder website for Bayes factor calculators, or Richard Moray's R package, which are really all the same. They use something called a Cauchy, or half Cauchy distribution. So let me just show you what that is. The dotted line here is a normal distribution, and here's the Cauchy. You see the Cauchy is a sort of a bell shape, much like a normal. But what distinguishes it is it has these thick tails coming out, very thick tails. So what does that mean? Well, just as when we're talking about the normal, I said the standard deviation is a sort of a scale factor telling you the sorts of effect size you're expecting. And if you go out 2 standard deviations, or twice the scale factor, you have 5% of the area beyond it. So let's call that a rough maximum. If we use the same rule with the Cauchy, and you specify a scale factor R, then the maximum is about 7R because of the fat tails. So how does that affect things? Well, that's actually something that can be relevant to making a scientific judgment about how to model the situation. So if we go back to this case, where this initial study, I just pulled these numbers out of the air. I hadn't thought about it further when I wrote down the example, but I said there's 20 seconds versus 25 seconds in the initial study, so a 5-second effect. you do something relevantly similar and think 5 seconds is expected. Now, if we use a normal distribution, I said about twice that is the maximum. So is 10 seconds a plausible maximum in this situation, just if you make a judgment about it, all things considered? Well, that will be increasing walking time from 20 seconds to 30 seconds. That strikes me as roughly a sort of plausible maximum. If you go 7 times that, it's 35 seconds. So that would mean, if you use a Cauchy, you're expecting the control group to be out 20 seconds and the experimental group after a flash to be 55 seconds. That strikes me as rather implausible. I mean, we've gone beyond the realms of a plausible maximum in that case. So in this example, the normal or half normal would be scientifically more appropriate than the Cauchy. Do you see how that's a scientific judgment, as it were? You look at the paradigm and you say, what actually is plausible here? I don't know why twice the scale factor comes up. When I first saw that, when I was writing my book in 2008, it was a little bit arbitrary, isn't it? And it can't be a law of the universe, but it does seem to satisfy my intuitions in a surprising number of cases. So that's why I offer it to you as a sort of a default to consider. And if it doesn't fit your intuitions, we have other options. It's not as if one's forced to accept that at all. The Cauchy go is 7 times.
Sorry.
Yes.
Is that why you specified for the Cauchy? Is that why you specified the width? I mean, with that.
Yeah, when you say well, on the router package, you specify scale factor. You put in the R. Yes. Or.
So the scale factor is essentially width.
Yeah, it's sort of the equivalent of the standard deviation, except Cauchys don't apparently have standard deviations. It's called scale factor. It's a very unusual distribution, but it's sort of the equivalent of the standard deviation with the normal. So I sort of tried to think of a situation where I thought, I've always found the normal, I've never used the Cauchy, and I've always found the normal more appropriate. But as I say, that can't be a law of the universe. And so I thought of a situation with this example where a Cauchy may be more appropriate. So let's say the control group actually went from 20 seconds to 21 seconds. That's what I changed. So it's a 1 second effect. And then you got elderly people to walk down the corridor, and you found real elderly people took 30 seconds. Well, that's got to be 30 seconds would then define a maximum, and surely they wouldn't walk slower than elderly people really do. So given that the effective of the control was only 1 second, and the prime people could go more than 22 seconds, surely, maybe the Cauchy would be appropriate in this situation. Yes?
When you're setting a maximum, is it kind of better to err on the side of setting too high a maximum or too low a maximum?
So remember the point I said for the lunch lecture, that the vaguer your theory, the more the theory is penalised, and the easier it is to get evidence for H0, therefore. So when you set a vaguer maximum, what you're doing is you're making it easier to get evidence for H0. So which side is the best to err on? I would say it depends on what you're trying to do. So if you wanted to get evidence for H0, I would say it's best to err on the other side. And if you wanted to get evidence for H1, it would be best to err on that side. So that to the extent you've made an arbitrary judgment, you've made sure it works against you a bit. Obviously what is best is you didn't err on either side, but you got it right, so you can trust the evidence that you got. But given that is going to be difficult, I'd say try and get as close as you can, then err on the side that works against you, because then nobody can argue against your conclusion. One thing to think about the Cauchy is, in this respect, is the JASP and the Rauder and the Moray calculators deal with standardized effect sizes, Cohen's d. So when you set the scale size, the scale factor, you're talking about how many Cohen's d's are you expecting, standardized effect sizes. Okay. So if you said it was 0.7, Cohen's d of 0.7, which is sort of their default setting, what you're saying the maximum is 7 times that. Okay. 4.9 are about 5, a Cohen's d of 5. So you're saying a plausible maximum is a Cohen's d of 5. You might wonder if that really is a plausible maximum, or if your plausible maximum, as I said, very hard to get a Cohen's d more than 1 in most cases. Not always, of course. Learning experiment, you can pump up your Cohen's d as much as you want. So now with big data, with very large n, you may get evidence for a very small Cohen's d. So actually, and I know this is meant to be our big data, which isn't something I thought a terrible lot about, so my examples haven't been very big data-ish. But when I think about it, the maximum plausible may indeed be considerably larger than the estimated scale of effect when you're dealing with tons of data, right? So Cauchy may well be more important than I've personally found, because I'm just a humble cognitive psychologist who runs 30, 40 subjects. You're dealing with tens of thousands of data points or subjects. Things might flip round to Cauchy being rather more important. But that's, as I say, that's a scientific judgment. And what you shouldn't do is just take something off the shelf and just go with it. You've got to look at that model of H1 and say, does that really apply in my case? And the sort of the tools I've given you to do that is to say, what's the scale of effect? Set that. And what's the maximum? The ratio between them tells you what distribution to use. And the scale of effect you should get from something you can point to. Other data, ideally. Okay. So you're informed. So now let me go through how you might go about thinking about getting this model of H1. Before I do that, just tell me how to use my calculator so you can play with it as we talk. So now in a t-test situation, you need the same information from the data as for a t-test, the mean difference and the standard error of the difference. And that just what a t-test is. It is the mean difference divided by the standard error. Or it's the regression slope divided by the standard error. Or it's whatever parameter you're trying to estimate divided by its standard error. So what that means is the right standard error for that thing you're trying to estimate, for that difference or whatever, is the mean difference divided by t. So if you run whatever package you use to get your t, you can get the right standard error out by this simple rule. Well, it might give it to you anyway, but at least, for example, let's say you're reading papers and you want to do a Bayes factor. Often use that. There's a t or something. There's the mean difference. I can get the standard error out easily. Note also that any 1 degree of freedom f, 1 degree of freedom in the numerator, is the same as a t. You square root the f, you get a t. So, and any 1 degree of freedom f can be treated as a t. It might be a 3-way interaction, it doesn't matter. It is actually a t value, so we can do whatever I'm going to go through in all those cases. So that's just reiterating. When we get a b of about 1, the data is equally well predicted by H0 and H1. So that's when you're not going to use those data to count against any theory. But as long as we pass some threshold. So I've put 3 here, and I use 3 myself so that my p-values align as closely as they possibly can do with my Bayes factors. And I'll be interpreting with respect to Bayes. Some journals are talking about what would be a good threshold for Bayes factors. So a couple of them are reckoning they might go with 10. Cortex will probably be going with 6 for registered reports. It's currently 3 for registered reports. We'll probably move to 6. But if you do that, you have to change the p-values to make it fair, you see, for people doing significance testing versus Bayes. So the rough correspondence is if you're going to use a threshold of 6, you should use a p of 0.02. If you're going to use a Bayes factor of 10, you should use a p of 0.01. Then that as much as is possible, because there's no guarantee of correspondence, as much as possible. That makes equal playing field for both. I think, like I mentioned, 3 we should interpret as starting to be worth taking note of, or this will be worth checking up on more. I think that should be more the feeling of a 3. 6 is more getting there, I think. I think we should switch to 6 and 0.02 more generally. When you have a base factor of 6, there's less reversals of evidence. Errors are less. It's stronger evidence, twice the amount of evidence. So to get a Bayes factor, Google my name. Probably the first site that comes out is the right one. It should be a picture of me with a yak at 5,000 meters. You'll see, click here for a Bayes factor calculator. And you get my Bayes page. Scroll down and you see big red writing, click here to calculate your Bayes factor. You'll then get a Flash program. It was put up about 10 years ago now. Some people just in the last week have been saying when they click on it, it hasn't been running as a Flash program. I haven't pinpointed that problem yet, but what they say is it does work on some browsers and not others. So I'd be interested to know if anybody does have a problem calling it up, and if so, if you switch to another browser, whether it does work. And I don't know if that's a problem with Flash or it's a problem with more browsers having Flash blockers built into them to stop adverts doing invasive things. Oh no, you see, that shouldn't happen. It shouldn't download something. It should just, a window should pop up. So I think some browsers are just in the last couple of weeks have put in some Flash blockers to stop adverts, as I say, which often use Flash. If you sorry, what was that? But hitting F5 and then it worked.
Yeah.
Oh, okay, that's interesting. So hit F5 and see if it. Yeah. Oh, that would be very. If that's a solution, then that's really simple and easy. Is everyone okay? They're getting up a pop-up coming with it. If you're not, if you press F5 and then does it work? Or try another browser if that's not working. This seemed to happen in the last couple of weeks, so I haven't tracked down the bottom of that. Is everyone okay? You're having, yeah. So we have a mixture of. Sorry. It does work in Internet Explorer, but not on Chrome. For me, it works on Chrome. But some people told me it didn't work on their Chrome, but it does work Internet Explorer. People tried Internet Explorer. If it's not working, is that working? So yeah, okay. Yeah, you don't want to download the Flash file. You want. What should pop up is this. That's what you should see on your screen if it's. Might be I need to reprogram it. Have it redone in some. F5 sorted it? So say again?
Just go for it. So when I was on Firefox, I was ever popular, I just wanted to.
So that was Firefox. That
was Firefox on Mac. I'm not quite sure why that one needed F5, this one didn't. But
yeah.
That was then downloaded. There's nothing different from what I had.
So someone next to someone in which it works anyway. All right, let's press on, and then I'll have a little look, maybe in the break, to see if we can sort it. So what you should get is a dialog box like this. What does the sample mean? It means the sample mean difference, or the parameter like the regression slope that you're estimating. So that's where you put in the mean difference. Its standard error would go in there. So that's how I told you to get it before. The mean difference divided by t is the right standard error. So that's the summary of your data, and that's a sufficient summary of your data. So you don't need to type in your data, you just need that summary of it. And indeed, I mean, if this was some complicated model you're doing, as long as you had a model parameter and a standard error, then you can just put in the model parameter where it's a sample mean and the standard error where it's a standard error, as long as the normal approximation can be assumed. Now, this is the distribution of the plausibility of different population values given the theory uniform? Yes or no? So it's asking, are we going to model H1 with a uniform distribution or not? And if you say uniform, yes to uniform, it says the lower bound, which by default I put in is 0, but you can play with that. And then the upper bound, which is the maximum you've identified, which could be due to properties of the scale, or just there's some condition where you say, well, I couldn't possibly do more than that. Okay, than the match controls or the whatever it is, or the people who really did it, or and so on.
That's in the units of the data?
Yes, exactly. You've got to make sure you use the same units throughout. Okay. Yes. And so when I said it's sort of easy, you're just entering here really 3 numbers. Right? You're specifying it's a uniform in this case. You put in your maximum, and you put in the mean difference, you put in the standard error, that's it. And you press go, and it'll tell you your base factor.
I was having problems. I think we've managed to solve this one.
Yes, how was it solved?
Chrome people go to about, what's it called?
If you go to HTTP /plugins,
You go to plugins.
About plugins.
and for Adobe Flash, choose always allowed to run.
Aha, I thought it was something like that. So for the purpose of this recording here, you go to plugins and say Adobe Flash always allow to run.
If you Google Chrome plugins,
Google Chrome plugins.
Or
About plugins, and always allow
and
Flash to run.
The hard refreshes.
Yeah, great. Thanks for that. Brilliant. So now, if you say no to uniform, then it assumes a normal or half normal. The default settings I have there for the mean of that normal or half normal put in 0. For the tails, that's this business of whether it's a half normal or a full normal. You put in 1 for the half normal, 2 for the full normal. Then you're left with just one thing to actually sort of specify in different cases, and that's the standard deviation, which is the effect size that you've gotten from the previous study or the meta-analysis and so on. So again, you're specifying the distribution, and otherwise you're just specifying 3 numbers. 2 to summarize your data, and then the 1 number for your effect size that you've identified from previous work. You click go and you get your base factor out. Okay, so that's the straightforward part. And now if we go back to the dance of the p-values, in which I've presumed that we had some information that 10 was a sort of effect size we're trying to pick up. So I put that in as a standard deviation for a half normal. And then for each of these p's, I've put down, given those assumptions, the base factors that go along with them. Now, one thing to notice is when the p is significant, 0.024 for example, the base factor is above 3. That's 0.024, base factor is 4. Here we have marginal very close to 0.05, close to 3. Marginal result 0.08, bit less than 3. So you see there's this rough correspondence there which is what Jeffries had said way back in 1939. But now, the interesting thing about the Bayes factors here is, well, as it happens in every case, although, as I say, there's absolutely sort of no guarantee that this happens. In fact, we'll know Bayes factors will sometimes make mistakes, of course, because it's statistics. If a Bayes factor never made a mistake, we'd only need to make one observation and calculate the Bayes factor, right? And evidence of 3 isn't that great amount of evidence. But nonetheless, see how much better it makes things, even with a criterion of 3, and even given what I just said. When we get this initial simulation, p equals 0.23, if you got p equals 0.23, you'll probably think, oh, my experiment failed. What have I done wrong? Why isn't there an effect there? What do I need to do to change it? But what is the Bayes factor telling you with 1.73 here? So is the evidence more for the theory or more for H0? It's actually more for the theory. You should actually, by a small amount, increase your confidence in the theory as a result of this non-significant result. But not by much. It's basically saying he was insensitive. You should collect more data. And as we go through, you see, I've called it the Tai Chi to emphasize something more gentle going on. Whereas, as Jeff Cummings says, that the dance of the p-values can make you manic depressed as you go up and down with each significant, non-significant. You get a far more gentle experience with the Bayes factors. Because whereas non-significant in this case, just as it happened, I didn't cherry-pick this at all, it said it's insensitive. Don't think your experiment failed. You need more data. Suspend judgment, as Fisher might have said. Okay. One thing to notice as well is the Bayes factors don't scale how you might expect if you're used to t values, for example. Because sometimes people email me and say, I've got a Bayes factor of 1,000. Have I done something wrong? Or 10,000, 50,000. I say, no, Bayes factors do that sort of thing. So don't worry about that. Okay, so what I want to talk about is ways of modelling H1, or how to think about going about that process. Because that's the all-important step. Because your Bayes factor only tells you something about your theory if your model of H1 is a good representation of your theory. Right? If you haven't actually represented your theory, then the Bayes factor doesn't tell you anything about your theory. So this is the point where you can criticize someone else's Bayes factor, or someone could criticize your Bayes factor. They could say, what's this got to do with your theory? Right? And this, I think, is the main criticism of Bayes factors that is out there. But as long as you make sure your model of H1 is a good scientific representation of your theory, you're covered from this criticism, as long as you feel you can justify it. Right? So you give the reasons for why you chose this model. That's the value that they got, so that's why I put it in as a standard deviation. So these are the sorts of approaches you can go through, and I'll talk about them. Use a similar study to predict another, like in a replication. Well, that's what I went through with the very first one. So maybe I'll skip over that because we've been through that. But I do want to say one thing: that there is one way you can cheat with Bayes that is surprisingly tempting to do. So let's say you had a theory that if you have seated in a high position, looking down on other people makes you feel powerful. So you put people in different seats, or different positions, and they rate how powerful they feel. And indeed, you find a difference of 0.3 units on a feeling powerful scale, where the people on the high seats feel more powerful than those on the low seats. So that's the data. Difference of 0.3 units, and you say, well, I don't know what my theory predicts, but look, I've got an estimate of it here. Why don't I use that as one of my assumptions and put that in other words, as the standard deviation of my normal or half normal. Now the problem is with this is this is double counting. You've used the same data twice. You used it as an assumption in making a prediction, and then you've used that prediction to test the very same data. So that's why that's wrong. The mathematics doesn't work when you use it twice. So you need You can't use the very mean difference you got to predict that mean difference. Okay, so just bear that in mind. So some people have said, could I use the confidence interval I got and put that in? Well, no, because that's the same thing. Okay, I couldn't have put a normal that went around to that confidence interval, because I'm just using the very same data to predict itself. So do bear in mind that would be cheating from a Bayesian point of view. Now, it might be that the prediction is 0.3 units because some other study got 0.3 units, a relevantly similar one. Well, that's fine because you've got an independent reason for postulating it. Okay, that's the point. So yes.
I think you should just eventually to use, or it was not implied, maybe it would be possible to use the control group value or control group mean as a possible maximum difference.
Yes. So now you can use data. You can use other data from the very same experiment. You can use other aspects of your data. You just can't use the very mean difference itself to predict itself. You see, because the control group data are, in a sense, independent of the, in some sense, it's irrelevant which one you collected first. They're just independent data. And as you see when I go on, sometimes I use other aspects of the very same data to help constrain things. And sometimes that can be helpful, but I'll never use the very mean difference itself to predict itself. So here, I will go through this example just to illustrate the use of contingency tables. So you can see, because this often comes up in research. So let's say a 5-minute talk is given to one of two groups about the harm of smoking. And it was a bloody good talk, because if you look at this, we get afterwards, we have an effect on the smokers have been turned to non-smokers. And so if we calculate an odds ratio, which is the product of that diagonal, 19 times 22, divided by the product of that diagonal. Because you see, if there's an association, things should accumulate along diagonals, one diagonal more than another. So that's what that's measuring. And statisticians like odds ratios as a estimate of effect size for contingencies. It has properties like being insensitive to the marginal means. And for me, that's great because if you take the log of it, it's normally distributed. So therefore you can use a normal approximation, therefore you can use my calculator. And it has a known standard error, which is sort of easy to remember. You just go, the squared standard error is just 1 over 19, just 1 over the sample counts. 1 over 19 plus 1 over 10 plus 1 over 14 plus 1 over 22. So square root that and you get a standard error. Now if you divided the log odds ratio by its standard error, because of the normal approximation, that's a z-score. You can look up the significance, and you get a p-value out that's extremely similar to the p-value you would get from a chi-squared test of independence. The trouble with the chi-squared test of independence is really just a p-value generating machine. And if you don't like p-values, that doesn't give you much. But when you think in terms of the odds ratio here in this way, you can generate p-values. So that's great, you get out your p-value, but you have an estimate of the effect size, and that's the important thing. So then you do a conceptual replication. You say, I know what, instead of giving the talk, we'll write it up in a pamphlet and hand it out to people, because that will be much easier. And if that did the job, then we don't need to send speakers around. So in this replication, you get this. You get an odds ratio of 1.42. As you can see here I go through exactly the same process, and it's non-significant. Now, normally the temptation will be say, well, we can't use these pamphlets, we have to have speakers. But you know that that's completely illegitimate, and the non-significant result by itself means nothing, and you would never dream of drawing a conclusion just on the basis of it being non-significant. So what shall we do here? Well, obviously we calculate a Bayes factor. How should we model H1, do you reckon? Using the previous study, right. So if we think that the pamphlet might be as good as the talk, why don't we just use the effect size from the previous study and put that in as a standard deviation. So if we do that, that's the model we'll have. Put in a half normal because we have a directional prediction. We'll put in the previous study effect size as the standard deviation. And the Bayes factor, the H means half normal, standard deviation 1.1 is 0.78. So what does that mean? It's pretty close to 1. It's insensitive, really. We need more data. So we should go out and hand out more pamphlets. Right? We shouldn't conclude that the pamphlets are ineffective. That's the crucial thing that we might be tempted to do. On the other hand, let's say the original study was a talk and the pamphlets. I just change it. And still had the same strength of effect. And in the conceptual replication, we only hand out pamphlets. So do you think we would change our model of H1 in this case? Well, see, now we're doing a sort of half of... Yeah, exactly. Now my temptation to say the original study defines a maximum more than the right scale effect because we're just doing part of the original study. So I think it would make sense to use a maximum up to 1.1, just do uniform up to 1.1 would be the simplest way of doing that. If you do that, actually it doesn't change things much. And in some ways this is the reassuring things about doing Bayes factors. Often it doesn't matter too much exactly how you've modelled the assumptions, as long as your models are fairly close to each other in terms of the intuitions that they're implementing. Now, sometimes you don't have a very specific previous study in mind. You might, let's say you're interested in what are the correlates of mindfulness or some personality measure or some AQ or whatever it is you're interested in. Now, and in the literatures I know when we deal with these questionnaires, the correlations are between about 0.1 or lower and up to about 0.5. And very rarely would you get correlations about 0.5 between questionnaires that, or even a questionnaire and something else, where there's real substantial question going on. It's not, it's not two mindfulness questionnaires or something. It's something that's of genuine substantial interest. And in fact, 0.5 is roughly a Cohen's d of 1, okay, or just a little bit smaller than that. So I reckon in many cases, if you're talking about substantial questions and you're looking at correlations, of course this is scientific judgment, but I'm just offering this, correlation more than 0.5 is pretty unlikely in many situations. Of course, you have to consider your own particular area to make that decision. So for a new postulated correlate, like the capacity to have flow experiences or something, I don't know if that is new in the mindfulness literature, but let's say it is, I would already have a feeling for what would be a plausible model of H1. I would know, well, probably plausible scale of effect is about 0.25, 0.2, 0.3. I really doubt we're going to get correlations more than 0.5. And that enables you to get going straight away. So in many areas, like questionnaires or indeed more generally than that, you can have a feeling. Now, you'd have to back that up. But probably as you're just sitting there at the computer, you would have an idea already, then go and look at some review papers or something and make sure you do back it up with something you can point to so that your decisions are justified by something objective that you can point to. Now, correlation in itself is not normally distributed. But Fisher came up with a way of making them normal, which is the Fisher Z transform. So the Fisher Z transform I've given here. And anyway, anyone who wants my slides, you're welcome to have them. And obviously it's on the recording as well. Now what this transform does, correlations between about 0 and 0.3 remain pretty much the same. And as you get more than that, it starts stretching them out. Okay. So before using my calculator, Fisher Z transform any correlation. And if you're saying 0.5 is a maximum, Fisher Z transform that as well. So as you were saying before, you need the same units that are going in. And Fisher told us what the standard error is. It's 1 over square root degrees of freedom minus 1. So we have a known standard error which you can enter into the calculator. So you can do correlations in the calculator easily. Now, some suggested the base factors for correlations put a uniform from 0 to 1 for correlations. I think that's making things a bit too vague. That will, when you make model of H1 that vague, where you're saying any correlation between 0 and 1 is equally possible, you're going to increase the tendency to get evidence for H0. Whereas I think we probably know in a lot of situations you're really not going to get correlations above 0.5. That's a matter of scientific judgment. So for me, I'd prefer to go this route than saying, well, the scale goes up to 1, I'll do a uniform from 0 to 1. In any case, when you Fisher Z transform, you can't put a uniform from 0 to 1 because 1 is stretched out to infinity. But this can also be useful if you're combining studies or dealing with standardized effect sizes, meta-analyses, or something like that. You can use my calculator at the end of it. I will go on to say, though, I'm not a great fan of standardized effect sizes, and we'll see why as we carry on. All right, and here's something else I offer. With fMRI, well, the concept is more general than this. It's you set up a standard where you say, from past literature, I know the sort of effect I'm looking for is probably some proportion of the standard. Like some control group might, or some baseline measure might be this amount, and you know that sort of a quarter of that is what you expect. Maybe, I don't know, a quarter, the guess responses will be about a quarter, guess response accuracy or familiarity accuracy in a recognition test will be about a quarter of recollection accuracy or something like that. Because then you can scale your predictions according to other aspects of your data, you see. Well, now in fMRI, people say, well, I don't know how much noise I'm going to get when I rerun an experiment. The noise is all over the place. It just depends on, I don't know, temperature or atmospheric pressure or other things. Well, one thing you could do is to build in a reference contrast. So you say, well, here's something that I'm pretty sure gets an effect, and in this area with this particular contrast. And if you had some idea from previous literature that, well, given that area, this is hippocampus or something, well, this area I expect about the same effect or half the size of effect or whatever it is, you can use the reference to set your predictions in a given case. There is another solution, which is you don't use standardized effects like regression coefficients. You use raw effect sizes. Because then the amount of noise, it doesn't matter. The base factor will just tell you got more noise, it's less sensitive. You see? And I'll go on to consider that later. Now, a very similar sort of strategy is to just find a basic effect and say, well, that's the sort of magnitude or scale of effect we could get if we manipulated it, if we intervened on it. If there's some intervention. So in this paper, I came up with a learning task, it was a new learning task we came up with that we didn't know how big the learning effect would be. There was no relevant similar study to say what could we expect. So what we did was to run a pilot to get just the amount of learning. Now what I was actually interested in was the effect of mood on the learning. I thought sad moods would affect one component and happy moods would affect another component. But in the pilot we didn't do any mood manipulation. We just looked at the amount of learning. And I said whatever the mood manipulation does, the amount of learning is the right scale of effect. Okay? And then that was put in as the standard deviation of the half normal for all tests. So that's something you can do. So notice this wasn't running the experiment and then running it again using the first one to estimate the second one. It was just a small pilot just to find out the amount of effect there is to play with and saying if we now play with it, that's a scale of change that we could bring about. In this study, it was an implicit learning task, artificial grammar learning, where we had a number of manipulations to do with gender and attractiveness. It involved a three-way ANOVA, and we just took the overall average amount of learning as a scale of effect that we used for the standard deviation for every single test. Three-way interaction, two-way interactions, main effects, simple effects, and so on. This was the very first paper, by the way, and it implemented my policy of a B for every P. So as a reviewer going through it, when we used this particular way of modelling H1, it turned out, which is rhetorically useful, that whenever the B was around 3, the p-value was around 0.05. So although we're interpreting with respect to the B, the significance testing would say, in the case of significance, I would say there is evidence for a main effect or evidence for an interaction. The significance test would say, yeah, I see that, yes, I agree with that. But then when it was non-significant, I'd say peculiar things, or we would say peculiar things like there was evidence for no interaction. And the significance test would say, well, I suppose it's a slightly funny way of putting it, but it doesn't contradict what I'm getting from the p-values. Or I would say there's no evidence one way or the other for whether there was an interaction. So I was making a discrimination that the significance tester wasn't able to make, and yet didn't contradict what they would conclude from the data either. But was very important for the discussion in theoretically, deciding what the results meant.
So for things like interaction, do you just do the contrasts?
Yeah, I'm going to take you through an interaction so you see how I did that. Here we go. So these authors were interested in whether process experiential therapy, PET, was as good as CBT in treating depression. So on the BDI, Beck's Depression Inventory, those given CBT, that was their pre-score, they had the CBT, and that was their post-score, and so the change was 12.5. And then for PET, we have the same, the pre-test BDI, the post-test BDI, and the change 11.45. Now they wanted to argue for equivalence on the basis that the interaction time, pre versus post, by type of therapy was non-significant. So the F for the interaction, the 1 degree of freedom F, is 0.18. Now, so how do we do a base factor on that? An interaction, two-way interaction, is a difference of differences. That's what it means. So we've got the differences here. We just find the difference of the differences. And that is the raw effect size in BDI units for the interaction. We square root the F to get the T. Remember I said any 1 degree of freedom F is just a T squared. So we square root the F to get a T. Now we can find the relevant standard error just using that formula I said before. It's the effect divided by the T. Right? So that's the relevant standard error for that effect. So now you've got what you need to type into the calculator for the interaction. So this is a direct test of the interaction, not just of simple effects or something like that. But a 1 degree freedom effect just is a contrast. So in another sense, this is a contrast, but it is the interaction contrast. So now how shall we model that? Well, let's say you're a CBT chauvinist and you say, whatever a therapy does, it's not going to be better than CBT. Now, come on. So if we wanted to show equivalence with that assumption, we can say, and this comes back to my point about using an aspect of the data. We could say, well, this is about 13 here, the change the CBT produced. So we're going to use a simple effect now to inform us about the interaction. We say, if PET produced no effect whatsoever, it was utterly useless, then the difference of differences will be 13. So that's the biggest effect we could get. On the other hand, if PET was equivalent to CBT, then the difference of difference would be 0. So the interaction effect must go between 0 and 13. So this is a little trick you can use to get out interaction effects. Indeed, if we assume that, we get a Bayes factor of 0.36. Notice I've notated a U for uniform, and I put in square brackets to indicate an interval that went from 0 to 13. So you've specified the model. Now 0.36 is actually reasonably good. It's not quite the convention we said of 0.33, but I think the way to think about these conventions is not, because remember, what the Bayes factor really is a continuous degree of evidence. There's not like there is some sharp change at 3. So a better way of thinking about Bayes factors than, say, a sharp threshold, you say we have at 0.05, is a bit more like Cohen's D. Because Cohen gave us sort of rough criteria where 0.5 is a medium effect size, 0.8 is large. But no one's going to think 0.45 isn't quite a medium effect size yet, or 0.49. And you only get to medium when you go to 0.5. No one thinks that. So think about Bayes factors more in that way, that we have rough marks or guidelines, but it's not as if anything dramatic happens at those points. Of course, an editor or reviewer might say to you, we have tough standards and it needs to be less than a third for the purposes of journal hygiene and so on. But just bear in mind for your own interpretation that 0.36 really isn't that different from 0.33. But I did say 0.33 or 3 isn't really that great evidence anyway, so it'll be nice to get more evidence, but this is pushing up against being worth taking note of and certainly worth exploring further. So what about interactions with more than one degree of freedom effect? So here's one to do with the Stroop effect. So the Stroop effect, you have a congruent condition where people are particularly quick to say what the colour is, an incongruent condition where you're slow, and a neutral condition where you're in between. So you have to say what the colour of words are, and the words can be coloured words or non-coloured words. Amir Raz in Canada showed what surprised me at first was if you give a hypnotic suggestion to highly hypnotizable people, that the words they see on the screen will be meaningless script in a foreign language. That this halves, at least, the Stroop effect. And it does it by reducing the incongruent reaction time, which is what surprised me. I mean, I could imagine a highly hypnotizable person just being slow all round to make sure they even out everything, but it sort of more or less selectively reduced the incongruent reaction time. I must admit I was rather taken aback by that, but I've replicated a number of times, even though I didn't believe it at first, at Sussex, so whatever the explanation, I take the effect to be genuine. So how would we analyse this with a Bayes factor? My favoured strategy in almost all cases is to go for 1 degree of freedom contrasts, because they generally pinpoint particular questions of scientific relevance. So when you have more than 1 degree of freedom here, you can generally decompose it into a set of relevant 1 degree of freedom contrasts, and then we can do what I did before. So in this case, it happens rather naturally because there's Stroop interference and there's Stroop facilitation. Okay? And theoretically, Stroop people say there could be different mechanisms underlying them. So in fact, it's pretty useful to separate these things out. So if we take interference, which is the incongruent minus neutral, we have a 1 degree of freedom interaction. So we have it for no suggestion. We have a difference for no suggestion, a difference for suggestion, and the difference of the differences is the raw effect in milliseconds for that interaction. So then we can just go through the very same process that we went through before. That is, we could say, whatever the effect of the suggestion, what it will do is if it does anything, it will reduce the interference, maybe to 0, in which case the difference of differences just is the interference we get in the no suggestion case. Or it doesn't touch it, the suggestion is useless, in which case the difference of differences will be 0. So again, we can put a uniform from 0 to the interference effect from the no suggestion case. So we're using one of the simple effects to fix the interaction effect. And again, we can use the f for the interaction square root to get a t, and that gets our standard error. So this turns out to be a fairly general procedure for looking at interactions. Incidentally, I could just go back to, here, the CBT case. If you wanted to allow PET to be more effective than CBT, we could have the uniform just extend in the other direction. See? And we can do it by the same amount for symmetry. And in fact, in that case, we get a very similar base factor, reduces it just a little bit more. I did have the exact value there, but I've taken that off. Now, actually, I've been talking for a bit over an hour now. Shall we have a coffee break for 5 minutes? And so you can perk yourselves up a bit before we carry on. So what I'm going to do is talk for another half hour. Then we're kicked out. And so there's a hard limit on how much I can talk. But that means we have up to an hour out there. And what I suggest we do out there, well, one is just general questions, but also go through any data that you have that you might want to try base factor on. And I'll be around to answer questions and make sure you're doing it right and getting informative answers. So now let me quickly run through other ways of thinking about little tricks that I've just used over the years in order to help myself model H1. I don't know if anyone here interested in metacognition and the extent to which, say, confidence can predict accuracy. Yeah? Okay, good. So I've been interested in that from the point of view of being interested in implicit learning, subliminal perception, because under certain conditions, one could argue if there's no relationship between confidence and accuracy, there's a case for the knowledge being, or the perception being unconscious. And I've been merrily, even though in fact I was taught Bayes at Oxford when I was a PhD student at Oxford by Jonks, or John Kier, who would come and teach us every Wednesday, and he would come and teach the psychology postgraduates every Wednesday afternoon. It was optional whether we went or not. He decided to put on a term of Bayes, and at the end of the term there was just me, one other student there, Miles, and everyone else had said, oh, this has nothing to do with my thesis, I'm off. But I found it fascinating, and my first conference presentation around about 1990 involved giving Bayes factors. And then I was interested in it but forgot about it. I just got on with things you need to do for your job until about 2004. So in that intermediate time, I guess I didn't take on board the lessons I should have learned and was merrily using non-significant relationships between confidence and accuracy to assert there was no relationship between confidence and accuracy, and therefore there was a case for subliminal perception and unconscious knowledge going on. But as you know, I was completely wrong to do that. Now, in the case of the relationship between confidence and accuracy, there's sort of theoretical or statistical reasons, statistical results we can use to help us with the modelling. Now, in terms of the person's accuracy on a task, say a perceptual task or a memory task, is it old or new, present or absent, you can express their accuracy with D prime in signal detection theory. And we can call this type 1 D prime. Type 1 meaning it's about the world. So you're saying, in the world, was the light shining or not shining? Okay. Was that stimulus presented or wasn't it presented? Old or new? Okay. So we call that type 1 D prime. Now, type 2 D prime is not so much about the world, but about your accuracy, about whether you have knowledge or not, or are you just guessing. So type 2 D prime is whether the person is confident when they get things right and not confident when they get things wrong. So can they discriminate right from wrong? Can they discriminate their own accuracy? Now, better than what is normally called type 2 D prime is something called meta D prime that has more desirable properties, for example, in terms of not being sensitive to variance inequality. Now, meta D prime has a hard limit in that the population value is not more than the type 1 d prime. So now that's really useful. And type 2 d prime, although it can go above that, under normal conditions tends not to. So what you can do is, when you're measuring metacognition with a type 2, or the best sort is meta d prime, is use a uniform from 0 up to type 1 d prime. So you don't need to think any more about it than that. Meta d prime can't be more than their first order performance, the performance on the world. So just use that as a uniform. As I say, just with a subliminal perception experiment we had, unfortunately, even though the relationship between confidence and accuracy was non-significant, the Bayes factor was 0.36, even on meta-analysing all the experiments in the paper. So the evidence was getting there, but it wasn't quite as solid as I would like, using that method I just talked about. Now, sometimes what you have to do is calibrate with other data. As I said, Bayes sometimes motivates you to get other data, but it motivates you to get that because it's genuinely relevant to answering the scientific question. So something like subliminal perception, the logic goes like this. You've got priming of some sort, some effect of the subliminal stimulus that's significant. But the ability of the person to identify the subliminal stimulus in some test is non-significant. And then the syllogism goes, therefore it was subliminal. But such reasoning depends on saying, because the identification of it was non-significant, therefore they were non-significantly different from chance, therefore they're at chance. But that doesn't follow through. So if a person on some test of identifying the stimulus, performs at a certain level, 55%, 51% is non-significant, in order to interpret that, we need to know how well would they do if it had been conscious. We can't just pluck that number out of the air. We need to know what identification would be expected for knowledge or conscious. So if we wanted a really scientifically informed answer to the question, we better do an experiment where people say, for example, said they saw the stimulus, so we know it was conscious, and then we can find a relationship between identification and priming in the conscious case, where we have some evidence it is conscious because, say, people said they saw it. And then we can say, well, the priming was X in the subliminal case, so how much identification should be there if it were conscious? Now, I hope you see that that is extremely relevant, scientifically relevant information that we should have had anyway. I mean, we don't need to be Bayesian to see that that's relevant to knowing whether this was subliminal or not. And it's not a number plucked from the air. We didn't say Cohen's 0.5 or something like that just because Cohen thought that was a wonderful number. Right? It's relevant, it's scientifically relevant to answering the very question that we have. So then what we could do a Bayes factor, and I'll do a half normal with a standard deviation set to that expected amount. So in this case, thinking about Bayes factors has pushed me to collect data that I should have been collecting all along because it is scientifically relevant, but I only went about collecting it because I was motivated by a philosophy of informed Bayes factors. I wanted to do a Bayes factor and I wanted to be informed by the scientific situation. So let's say the priming was 5%. Significant. Identification 51%, where 50% is chance. Sometimes what you might have, and you look in the paper, is you don't have that full regression curve, which would be nice, identification against priming. But they might give a condition, you might find just a mean for conscious priming, and its mean conscious identification. Well, what you could do then is simply draw a line between there and 0, as a sort of not quite as good as the full regression curve. But what this would implement is the assumption that if it were all conscious, subliminal perception didn't exist, then they should go both to 0 together, putting aside noise. Okay.
So what if don't assume linearity? So I'm just trying to think about some psychophysical curve
Yeah, now this is making scientific assumptions, right? So you might dispute the assumptions like linearity or something like that. Then we can have a scientific argument about that, and you can say what your beta curve is, and that'll be brilliant. Okay, and then we get a better solution. So if conscious classification was 70%, and my calculator, by the way, presumes that the null hypothesis is 0. So in a case where the null is 50%, subtract 50 from your scores. That resets the null to 0. You see. So 50% is your chance baseline. Subtract 50 from your scores. So 70% would go to 20% then for conscious classification. The degree of conscious priming, let's say that's twice the amount of the putatively subliminal priming. Well, then this curve would say, well, take half the amount of conscious classification, so 60%, 10% above baseline. Okay? Is that clear to people? That's what I just said. So now, let's say mean priming was 1% above baseline. In other words, 51%, so it's 1% above baseline. So what you put in the calculator is 1%. You might want to do this now. You've got the calculator up just to check you know what you're putting in where. And let me say the standard error was 4%. So you can specify half normal and set the standard deviation to 10, because that's what we've estimated. People getting that? Now there's a little tweak I haven't told you that I want to tell you now. So what that Bayes factor of 0.45 is, that's just putting in the numbers that I've put there. But we should do a little correction, that if the degrees of freedom are less than 30, you correct the standard error and make it a bit bigger. That's on my website, the correction factor. It's 20 divided by degrees of freedom squared is 20 divided by degrees of freedom squared. 1 plus that, you multiply the standard error by that. Okay. So that will increase the standard error by, in this case, 1.05, a factor of 1.05. So you should increase the standard error when you use my calculator if the degrees of freedom are less than 30. So multiply 4 by 1.05 in this case, and that will increase the standard error a wee bit. You with me? Got confused? So, yeah. You can look at my website to go through. I mentioned that now. By the way, you can also use that. So if you're correcting for unequal variances or something, that adjusts the degrees of freedom. The way you do this adjustment is you then use the degrees of freedom the way that I've just said. If adjustment brings degrees of freedom less than 30, you need to increase the standard error according to the formula on my website. Now what that does when you increase the standard error, it moves the Bayes factor towards 1. It makes the data less sensitive and discriminating either way. So we can say this is insensitive, and if you did the adjustment, it would just be even more insensitive. Now I just want to say the difference between this and using a default. So you can get Bayes factors that just default to a certain value, and you just click on them, and they give you an answer, which will be tempting to use. So if you use the default Cauchy Bayes factor that JASP gives, for example, the default gives a scale factor of 0.7 for the Cauchy, and if you use that, you get a Bayes factor of 0.24. So you'd come to a... Notice that it isn't very different, actually, and that's one thing that is reassuring. It's not that different, but it's a difference that does matter when we're dealing with small amounts of evidence and discussion sections and editors and so on. So you do want to get this right. And the reason why the default Cauchy gives you sensitive evidence for the null is it uses a fairly vague model of H1. So the default Bayes factors are going to tend to give you more evidence for H0. In this case, getting evidence for H0 is to make a substantial conclusion about there being subliminal perception. So it's important. Right? So I'd say always go with informed, not with default. Now to give another example to illustrate why I would always go with raw effect sizes. This is contextual queuing. It's an implicit learning experiment where what you do is you search for a target and some of the distractor displays are repeated. And people are faster to find the target when the distractor display is repeated rather than new. So you get a reaction time savings from old displays. Okay, not terribly surprising. The claim is it's implicit because if you ask people to recognize whether an old distractor display is old compared to a new display, they can be non-significantly different from chance on a recognition test. Okay. So here's an example of a study. They get a 200 millisecond queuing effect. So this shows there was learning. The recognition test was non-significant. So you say, therefore the learning was implicit. But you know you can't do that. We need to know how well would people do on the recognition test if the learning had been conscious. So I looked for a study where they claimed the learning was conscious. So here's a queuing effect, and they get a significant performance on the recognition test. And if you look at Cohen's d here, it's about the same in both cases. So what we could do is, we have a much bigger Cohen's d here. We could say we expect the same size Cohen's d there. Okay, we're being informed by this other study. That's what I said you should be, is informed. So Cohen's d should be about equal. You can use Rauder's, Moray's, JASP Bayes factor for this because they deal in Cohen's d's. I set the scale factor to 2 for testing this recognition test here because this other study said Cohen's d about the same. That's the translation between them. The learning effect here to Cohen's d of 2. So let's say we expect a Cohen's d of 2 for the recognition test. That's our calibration. That gives a Bayes factor of 0.13. We say good evidence for null hypothesis. And if we did a default Bayes factor, 0.33, again, good evidence. So it looks like they've done, well, what I've done here is exactly what I suggest. Done a Bayes factor. We've used other studies to calibrate and inform ourselves. Yes, question?
What's the default Bayes factor?
Oh, that just uses a scale factor of 0.7. It's a Cauchy with a scale factor of 0.7, yeah. Just because the argument is psychologists are often interested in something about 0.5.
Right.
Okay. But there's a problem here, and I'll illustrate the problem by telling you something that you didn't know, which is the number of trials. On this original recognition test, there was one trial. In this Smith and Shank study, there was 48 trials, and the performance was 60% in terms of raw scores, not Cohen's d. And the performance here was about 60% in raw scores. Okay. Now, this is why it's important to use, I reckon, raw effect sizes. Because a Cohen's d is a measure of signal relative to noise in sensitive things like number of trials. You change the population value of Cohen's d by changing the number of trials, something that's theoretically irrelevant. Right? So what this would motivate you to do, what p-values motivate you to do, is to use as many trials as possible to get a non-significant result. But doing a Bayes factor on standardized effect sizes would also motivate you to use as few trials as possible on the recognition test. So both p-values and Bayes factors on standardized effect sizes, not taking into account number of trials, would motivate you to use as few trials as possible, which is obviously scientifically a nonsense. But if I do the Bayes factor on standardized effect on raw effect sizes, and adjusting for the different reaction times here, I get a Bayes factor that's insensitive, which is what you probably expect and should get if you're using only one trial. Now you could adjust your standardized effect size for the numbers of trials. You could take it into account. It's not that you couldn't do it, but it seems to me a lot easier just to deal with raw effect sizes from the start, because wherever there is a difference, it's the raw effect size that motivates finding the correct, scientifically correct answer. So when a scientific problem is properly formulated, Bayesian statistics incentivize finding the correct answer, unlike, say, p-values. Something else Bayesians sometimes do historically to get a model of H1 is they just survey experts and say, what do you think? What do you think we would get in this situation? Generally, I don't like that, because the expert just becomes a black box. So what do you expect? I expect this. Well, why? What's important is the reason why, scientifically. So I prefer to point to, well, this paper got that effect, this meta-analysis got that effect. So surveying experts isn't something I generally recommend, or just occasionally. I won't go through this for the purposes of time. It's useful. And in the case where I have done and have paper submitted is because clinicians had said, who used hypnosis, that different forms of hypnotic induction are differentially effective. Now, the only reason we believe that is clinicians have told us that. So it seemed to me the best way of getting an estimate of how much difference we should expect in response to suggestions is to survey clinicians and telling us how much difference we should get between the different hypnotic inductions. So in that case, surveying experts seem to me appropriate. You could look up this book, Uncertain Judgments, Soliciting Experts' Probabilities, if you wanted to consider some best ways of doing that. Anyway, when we did that, we found Bayes factors showed evidence for no difference between different hypnotic inductions. It doesn't matter how you induce hypnosis, as long as the subject understands it to be a hypnotic induction. Now, another approach that's in the statistical literature is taking a sample from your data to act as an original estimate. Okay. This is not an approach I like, but it is sort of in the literature, so I give it to you. And you might say, why not? In that, isn't it a bit the same as doing a pilot study and then running the main study? So let's say you have a bunch of data and you say, well, I don't know what to expect. Why don't I take a bit of my data and use that to estimate the effect size and then put that in the Bayes factor? The first question comes up is, what proportion of the data are you going to split off? Statisticians have looked at that, suggested square root n. Seems to sort of balance a number of considerations. So if you've got 25 subjects, you'd use 5 to generate an estimate. Well, which 5? Well, I suppose all possible sets of 5, or at least you could randomly sample that proportion a lot of times. And then you've got a whole bunch of Bayes factors. Well, what could you do? Well, you take an average of them. What I would do before taking the average, by the way, is take a log of them, then average, then anti-log. So you make the Bayes factor symmetric before you average. Now, you could do all of that. My instinctive reaction is an aversion to it, and I've tried to put my finger on why I have that aversion. One is it violates the principle, estimate an effect only after establishing there is an effect. Or maybe you could put it, use an estimate only if it's precise enough. Because sometimes when you select 5, you're going to get estimates that go completely in the wrong direction. They're going to be all over the place. I mean, why do I want to use some poor estimate to predict an effect? Or, to put it another way, why am I bothering with this poor estimate? I mean, what is the theory that I'm testing by doing this? Am I testing any theory at all? And if I don't really have a theory, as I was saying before, I say, why not just estimate the parameter values? Are you really in the business here of hypothesis testing if you have no theory? You have no grasp at all of what it is you're trying to do. Estimation, I think, is something you always do. So estimation you always do. But it might be that's all you do in some cases. You just want to check something, though. You need to check, if you want to conclude people were above baseline, that's not just estimation, that's, you want to reject the null. If you want to conclude people were different, so you've got to watch what you conclude. If you just do estimation, all you can say is, whatever follows from estimation, the parameter estimate is about this, and it's probably between these limits, that's it. And that doesn't even allow you to say whether people are above baseline or not. If you say your credibility interval or your confidence interval is above some baseline, and then you use that to say it's above baseline, that is exactly the same as significance testing. So that's why I say you can't do that. Now I just want to go through a criticism of hypothesis testing, why we're on it, because there is this debate between estimators, if you like, who say never do any hypothesis testing, you should just estimate, and that happens in the Bayesian world as well as in the frequentist world. I don't understand that really, because I think almost all of us genuinely have questions like, are people above chance? Is this group different from that group? Is the drug effective? And so on. We want to know the answer to that. But one of the criticisms they give of hypothesis testing, either significance or Bayes factors, is the point null is never true. So why are you trying to reject it? If it's always false. The point null is never true to the nth decimal place, no matter what you do. Well, Tom Bagley's textbook, Serious Stats, has this interesting example. There's an online experiment with about 28,000 participants testing for the existence of ESP. There's a chance baseline of 50%. And the confidence interval went from 49.6 to 50.2%. Well, what we can say from that is the point null of 50%, it's not exactly true, but it's pretty damn close to true. So I reckon if you are a good experimentalist with counterbalanced materials and so on, you can get a point null that is approximately true to a high degree of accuracy. Yes, if you're doing ecology or voting behavior or stuff in the wild, uncontrolled experiments, then maybe the point null isn't true. But if you're doing controlled experiments, it strikes me as often a good enough approximation. Why good enough? Well, this suggests that the true null in this case was somewhere between minus 0.3 and plus 0.3%. Okay? Probably even smaller than that, but at least it was within those limits. So let's say we got a result of 55%, Bayes factor of 4.27. You can use my calculator, by the way, to work out an interval null. I could show you how to do that outside if you're interested. Let's say the interval null is 0.5%, minus 0.5 to plus 0.5%. Except we don't know what the true null is, but because of not counterbalancing properly, I don't know, whatever it is, little mistakes or whatever, we can't say the point null is exactly true. Well, that changed the Bayes factor by less than 0.1. Now, any model in statistics is never exactly true. So the people who tell you, the estimators who say, the point null is never true, well, I say, we used a normal approximation there. The normal is never exactly true. Right? Your model of these variables being in the model and these not, and this being linear, that was never exactly true. Okay? So the question for a statistical model is never whether it's exactly true to the last quantum place. It's whether it's a good enough approximation. And this shows in many cases it would be a good enough approximation. In many cases. But now I'm just a humble cognitive psychologist used to dealing with 40 subjects or so. With big data and you're getting tiny effect sizes, I reckon specifying an interval null may be a lot more important. So you need to think about what is the minimal interesting effect sizes, have a interval null there, and you can put that in my calculator if you're dealing with big data. A couple of final points. One is if you have several studies, what you should do is combine the studies together. Well, you can find a Bayes factor for each study, but the way you get an overall Bayes factor is meta-analytically combine the experiments to get an overall mean in raw units, I would suggest. The standard error for that mean, then you plug that in the Bayes factor, then that will be the appropriate Bayes factor for the combination of your data. Okay? So it's simple to combine experiments. Just first get a combined mean, and there's a Flash program on my website that will do that and give you the combined standard error. This goes over that. Just saying there are these other Bayes factor calculators out there. That's the Rauder one, that's the JASP one. JAS at the moment just does Cauchy, but very soon it's going to have other possibilities, including everything that I've talked about. E.J. Wagemakers says that will be on JASP shortly.
My version of JASP allows entering skill vectors.
Allows.
Entering skill vectors. I'm not quite sure if that's the same. But there's an option like what is your prior skill of X to this.
Okay, yeah, I just got an email from JASP saying that they've just put in what do you call subjective priors, which means what I'm talking about. Informed priors, I think, is a much better term. So that might be in there already. Good.
Mine hasn't.
Yours? Yes. Good.
Seems to have something like that, something where you can put a skill.
Yes. All right. So I got through a lot of material very quickly with not many breaks to finish at 4. But now what we'll do is go outside, answer questions, and most importantly, I think if you could have a go at your own data, trying it out, and I can answer any questions. Thanks very much.
Thank you.